For laboratory chemists, understanding the behavior of nucleophiles and electrophiles is essential to developing new medications like antibiotics and antiviral drugs, or creating advanced materials such as polymers and nanomaterials. These reactions are at the core of how we design and synthesize molecules with specific properties and functions. And in this video, we'll explore how nucleophiles and electrophiles interact to form new bonds and transform simple molecules into complex structures. Nucleophiles are reactants that donate a pair of electrons to form a bond. We see nucleophiles often as negatively charged ions, called anions, or the electronegative atom of a polar bond, such as the oxygen atom in water. Electrophiles, in contrast, are reactants that accept a pair of electrons to form a bond. We see electrophiles typically as positively charged ions, called cations, or the electropositive atom of a polar bond, such as the hydrogen in water. Nucleophiles and electrophiles tend to be more stable than radicals in solution, as they're able to form strong ion-dipole and dipole-dipole interactions with solvent molecules. Thus, most reactions in solution involve the donation of an electron pair from one atom to another. As we discuss different types of electron pair sharing reactions, we'll classify them as either addition or substitution. An addition reaction is a reaction in which two reactants form a single product. New bonds are formed between reactants, and bonds may be broken within one or both of the reactants as the new bonds are formed. A substitution reaction is a reaction in which two reactants form two products. Bond breaking and formation occurs in a concerted fashion, i.e., at the same time. Let's look at our first example reaction. In a carbon to chlorine bond, the chlorine atom attracts the bonding pair of electrons most strongly. Thus, the chlorine atom has a partial negative charge, and the carbon atom a partial positive charge. The partial positive carbon atom is electrophilic, so it may react with a nucleophile, such as an iodine ion. A lone pair from the negatively charged iodine ion is donated to the carbon atom to form a new carbon to iodine bond. The carbon atom can only form 4 bonds. Thus, the carbon to chlorine bond must break at the same time as the new carbon to iodine bond is formed. The bonding pair of electrons are then transferred to the electronegative chlorine atom, forming a chloride ion. We call this chloride ion the leaving group. This reaction is represented using curly arrows, where each arrow represents the transfer of a pair of electrons and is drawn from the source of the electrons, the nucleophile or the bond, to the electron acceptor, the electrophile or leaving group. This example is a substitution reaction, as there's two reactants and two products. One functional group, the chloro group, is replaced by another functional group, the iodo group. To be more specific, this is called a nucleophilic substitution reaction, because the groups being swapped correspond to nucleophiles. In this case, the iodide ion acts as the reacting nucleophile. As we saw earlier, not all nucleophiles are negatively charged. For example, water can act as a nucleophile by donating a lone pair of electrons from the oxygen atom. In fact, many functional groups can be interconverted via nucleophilic substitution reactions. For example, the reaction of a halogenalkane with a hydroxide ion produces an alcohol. In these examples, we've looked at nucleophilic substitution. Let's pivot to contrast with electrophilic addition. Double bonds, like those found in alkenes, can act as a source of electron pairs, allowing them to react with electrophiles. For example, ethene, C2H4, contains a double bond between its two carbon atoms. When ethene reacts with hydrogen chloride, HCl, this double bond opens up and will ultimately allow new bonds to form between carbon and hydrogen and carbon and chlorine. This is an addition reaction, as there are two reactants that form one product. And in this reaction, the partially positive hydrogen of HCl is attracted to the electrons in the carbon-to-carbon bond. This attraction brings a pair of electrons from this double bond to be shared in a new bond with hydrogen. In the process, the HCl bond breaks due to heterolytic fission. Heterolytic fission is when a covalent bond breaks and both bonding electrons go to just one of the atoms. In this case, the bonding pair of electrons from the HCl bond are transferred entirely to the more electronegative chlorine atom. This produces a chloride ion and a proton, H+, although the proton immediately bonds with the alkene to form a new carbon-to-hydrogen bond. This is different from homolytic fission, where the electrons split evenly. Heterolytic fission will always produce ions. A common real-world example of heterolytic fission is the ionization of hydrogen chloride and water, where HCl breaks into hydrogen and chloride ions. In our reaction, the other carbon atom in ethene now holds only 3 bonds, and has a positive charge after losing one of its original bonding electrons. This carbon is now a highly reactive electrophile. In fact, this positively charged cation will react with a nucleophile, such as our chloride ion, forming a new carbon-to-chlorine bond using a lone electron pair donated from the chloride ion. The reaction between ethene with HCl is an example of hydrohalogenation, as both a carbon-to-hydrogen bond and a carbon-to-halogen bond are formed. Alkenes can also react with diatomic halogens to form dihalogenalkenes. These reactions are termed halogenations. In this example, ethene reacts with Cl2 to form dichloroethane, splitting up the diatomic halogen to bond to carbons on either side of the carbon-to-carbon bond. The reaction with Cl2, or Br2 or I2, is unusual since the electrophile is a nonpolar molecule. In fact, we'll see the halogen molecule gain an induced dipole as it approaches the alkene, and the electron-rich double bond repels electrons in the halogen. Electrons will move away from the nearest chlorine atom and produce a partially positive charge. This partially positive chlorine atom is then electrostatically attracted towards the carbon-to-carbon double bond. An electron pair is then donated from the carbon-carbon double bond to the chlorine atom. A new carbon-chlorine bond is formed, and the chlorine-chlorine bond is broken, producing a chloride ion. Similar to our previous example, this chloride ion then reacts with the now positive carbon and forms a second carbon-to-chlorine bond. We can see the whole reaction mechanism here. The reacting electrophile could also be an interhalogen compound, such as ICl or BrCl. In these reactions, the halogen-to-halogen bond is already polar. The alkene therefore reacts with the less electronegative atom, which has the partial positive charge. For example, ethene would react with the bromine atom of BrCl, forming a carbon-to-bromine bond and a free chloride ion. In summary, electrophiles and nucleophiles play a crucial role in driving chemical reactions. Nucleophiles donate electron pairs to form bonds, while electrophiles accept them, leading to addition and substitution reactions. We discussed specific examples of nucleophilic substitution, where a nucleophile replaces a leaving group, and electrophilic addition, where double bonds open up to form new single bonds. In electrophilic addition, we saw that bond breaking often involves heterolytic fission, a process where both electrons from a broken bond go to one atom, forming ions. These concepts are not only vital for your exams, but for the understanding of real-life chemical processes to design and synthesize molecules with specific properties and functions.